Thank you all. It's actually a pleasure to be here. So you've heard a couple of talks in the morning about how do you do ML. So I'm trying to go back to a little bit of the basics. Before that, so as Margaret mentioned, so I'm a research scientist, and I also lead a couple of machine learning teams in Google Research. That means I get to wear an academic hat, and also we work very closely with the product teams and trying to bring some of that to Google products at scale. And rather than boring you with all the nitty-gritty details of the techniques, I will share some examples of how we went about solving some of the problems, and in some of the Google products that you probably are using every day. So the title of the talk is Powering AI at Google Scale, and I said deep learning and graph learning. I will unpack that as we go along. But first off, just let me give you some motivation, right? So machine learning is used in a number of applications, but the notion of machine intelligence in day-to-day applications that involve language and text is not new. But what we've been able to do over the last 5 years or so have sort of surpassed what we could do probably previously. And this is primarily due to better models, better learning techniques, etc. One example is smart messaging. How many of you have heard of assistants? I mean, your Google Home, Alexa, whatnot. So one of the interesting applications, if you're using a Google phone, do you know about Smart Reply? Mm-hmm. So if you're using Google Gmail and you sort of scroll down to the bottom, you might see some suggestions pop up. This is like automated responses to your incoming email. So we're part of the team that originally built this feature. So I'll share what happened, how did we go about doing that. But this is one of the core features in Gmail and also in other messaging apps. And the fundamental problem we're trying to solve is how do you understand intents from user conversations? And then how do you respond to that? And how do you build models to do that? There could be a number of ways many things can go wrong. How do you do that at scale? How do you do this in a sort of user satisfaction sort of way where you're saying that you're not just putting some predictions in front of the user. You're actually trying to give them something that they can use, right? I mean, and it sounds cool, right? ML sounds cool, but at the end of the day, we actually want to satisfy the users. So this is launched in a number of products, from Inbox, Gmail, Android Wear. A broader problem is natural language understanding. So here the idea is you're not just responding, but you actually want to connect incoming strings of text, for instance, or conversations into assistive actions. So one of the features in Google now that you can see is if you start typing in, remind me to do something, X, right? Whatever that X is, it'll actually suggest some actions. Like for instance, if you say, remind me to call mom, in Inbox, it actually shows you an icon with a dialer, and it says, if you have mom stored as a contact, it will actually pull up the phone number. So with a single click, you can actually call the person. There are a number of examples of this. How do you remind to attend events? How do you do, something like, cancel your subscription service or even start up your subscription service? So all these involve natural language understanding at scale. And the problems are not very simple as here's a model that you do, get some data and train it end to end, and suddenly voila, it works. It doesn't work that way. Moving from language to vision. Today, Google Photos can actually understand a lot of concepts. So if you just search for beach in your photo library in Google Photos, it'll actually pull up photos of beaches where the beach as a concept exists in the photo. And it's not just things like beaches. If you search for honeymoon or abstract concepts, it's still able to recognize. So for that, we actually need to do image understanding. That means we need to understand objects in the images, relationship between those objects, and do this at scale and with very, very high accuracy. And it doesn't stop there, right? So you could think of experiences which actually doesn't just get powered by one modality, but you might have multiple things, where you have to do image recognition and you have to do text understanding or user understanding, and a combination of all these things to power some features for your product. Photo reply is an example which we built. And the idea is that, say, if you get an image like this on top, the assistant will actually sort of automatically give you suggestions and say, if you say a baby, it'll say, so cute. And with a single click, you can respond to that. And this is not captioning per se, because captioning means you're trying to describe the image. This requires understanding what's in the image, but also tying it to response intents, what are suitable for that. The bottom one is really cool, which my favorite. I don't know if it'll do that anymore, but if you see a video or an image of skydiving, it'll say how exciting and how brave, which is basically suggesting that, hey, somebody who does skydiving is actually brave. We should have added stupid as there as well, but we can't. But you get the idea, right? So you're trying to respond to concepts in the image. And all these require machine learning, but not just a single system, but multiple models at different phases. And we have to do this at scale. So there are a number of other applications. I'm going to just give you a few examples of these. You already heard about smart reply. Email classification is something so any sort of classification, document classification, right? So we have to build systems like machine learning systems. This might involve deep learning, but also other systems like learning techniques like graph learning. How do you connect emails from the same user to each other, right? I mean, so using those sort of relationships to build those systems. There are a number of works which we have published over the years, and all of these are also used in production. One of them, which I didn't talk about, is video summarization, and this is a really cool project we had where imagine taking a 1-hour YouTube video and compressing it into a 20-second GIF. So if you've searched for videos like cooking recipes and things like that, you know that most of the time, the person is talking for 50 minutes, and then you'll have the really interesting bits in the 10 minutes, but it's very hard to find out where exactly those happen, right? So this system actually basically ingests the whole video and actually strings together a GIF of the most interesting concepts. Okay, so these are some examples which probably motivate you, and I'm giving you some of the really successful ones, where it started from small ideas, but also for solving some core problems for Google products. But there are several challenges, and these are 3 of them, but I think these are 3 very important ones. How many of you think ML is all about building cool models using deep learning or any of the fancy techniques out there? Yes, 1, 2. I hate to break it to you, even at Google, we're at the forefront of machine learning. Data is the #1 issue or challenge. And if you don't pay attention to this, you can do all kinds of stuff. It might just work if your task is sort of very similar to what other people have done. But I would say pay very close attention to the data. And there are a number of challenges related to data. How do you collect it at scale, the right amount of data, the right type of data, whether it's noisy or not. Second is model complexity. Then you start thinking about how do you build models, right? I mean, for your task. Is it simple models? Do you take really deep models? How do you actually pick the right model for your task? And then how do you scale that to not just one device, but billions of devices, especially if it's a mobile-first application? There's another angle to this. There are different types of computation models, right? So we might have to do ML on the cloud. If you're just serving predictions using an API on the cloud, then all the ML happens in the cloud, and then all the inference also happens in the cloud. But as you heard Rishi mention, on-device ML, which is a new area, but going to be an increasingly important area for you. If you're building an app, right, which has to have some intelligence into it, on-device ML will become an important factor. And so then you have to figure out how do you take the models that you build on the cloud and translate that to on-device models. Or sort of have a combination of the two, right? When you have sort of some type of predictions, you might actually do that on the device. And then in other cases, you might actually delegate it back to the cloud. OK, so let's now dive into some of these challenges. How many of you have heard of supervised learning? OK, great, almost everyone. For those of you who haven't, when you hear machine learning being talked about in almost every blog, every forum out there, what they're referring to is supervised learning, most often than not. And what it means is to build a machine learning model, we actually collect labeled data. And the notion of labeled data is if you're trying to predict, let's say, do image classification, you collect a bunch of pairs of images and their labels, the object present in that. And you collect thousands or millions of these, and then you train a model, and then you do the prediction. What is the challenge with that? For those of you who work on, applications at scale or non-common applications, by that I mean there's some niche task that you're trying to solve. It's very hard to get label data or enough high-quality label data to build a good model. And the hardness comes in many factors, right? First of all, sometimes you have to pay someone to actually create that data for your task. that is expensive. It's also time consuming. And depending on how good the quality of that data is, your model can suck or it can do great things. So this is an important factor. People don't realize this factor, but data is actually the number one, thing you should pay attention to, even before thinking about what kind of models you want to build. So there are a number of techniques in the ML world that address this problem. Like, I'm just going to break it down into sort of a taxonomy of like what happens, how do you deal with the data problem, right? What paradigms of machine learning should you look at or consider if you don't have enough high quality data, label data specifically in large amounts, right? So one of the options is semi-supervised learning. And the idea is that you have some label data to begin with, but you have plenty of unlabeled data. And you're trying to combine both of these into building more robust models that can actually leverage the structure underlying the unlabeled data. Unsupervised learning is basically what you heard in the previous talk. You're not trying to build a model to make some predictions. Instead, you're trying to learn some representation of the data. For instance, if I take all the images in the world and learn some representations for those, like some sort of embeddings for those images. Now, later on, if you want to do some classification, you can actually start from that representation instead of starting from the pixels directly. Then there are some other, probably you've heard these buzzwords, you heard transfer learning, few-shot learning, and zero-shot learning. What happens if you want to learn a completely new concept for which nobody out there has ever built a model for that or collected data for that, right? Let's say it's a completely new concept. What can you do then? So few-shot and zero-shot learning aims to cover that problem. And the trick is you try to associate your concept with some known concepts, right? And you might have labeled data for those other concepts, and you're trying to leverage structure in this labeled space and to transfer some of that information. And in the transfer learning setup, you're trying to take models that are already pre-trained for task A and then transfer it to a domain in task B, right? And so there are all these techniques. There are a number of ways to do these things. I'm not going to go into details, but if you ever hear these, and if you wonder what these things are, what people are talking about, when they use these buzzwords, this is exactly what they're trying to do. What's common among all of these is we're trying to exploit structure in the data or in the model space, and then translate that to what works for a given task. So in all these unlabeled, or unsupervised or supervised, semi-supervised setting, it's like you're taking some unlabeled data, exploiting the structure, and trying to see, okay, how do you augment the labeled data to exploit that information? And so here's the typical picture. I already gave you some of the motivation, right? So the big problem is you have, let's say, image classification as a problem that you're trying to solve. You have labeled data, but that's very limited. Quite often, you have plenty of unlabeled data. I mean, take the internet for that matter, right? I mean, all the documents, all the websites in the world, right? They contain some interesting information, probably not all of which is related to your task, but a lot of it is. Now, how do you take this lots of unlabeled data, combine it with the labeled data to build a pretty good model, robust model? This is where one of the solutions, and this is what one of my groups actually does, is go for a semi-supervised learning solution. We have a machine learning platform that does this, but it's not just applicable to image classification or language learning. It's also used for fraud detection, user classification, a number of applications. So what you need to understand when you're building ML models is what might seem like, hey, that's probably suited for image class, but the underlying idea on how to do the ML, not necessarily the model structure itself, but the idea can be transferred onto new tasks. So in semi-supervised learning, what we do is we, as I said, take the unlabeled data, which is plentifully available, and this minimal supervision, which is the annotated data that you have, which might be curated by some, in-house or domain experts, and try to exploit that structure. One way to exploit that structure is to use graph representations. And this allows us to do a number of things. First of all, why would you choose graphs as a representation, right? I mean, if you think about any problem or any sort of ML problem, it's easy for humans to actually say that, hey, here are two objects or two data points. I can define a relationship between them. Whether it's a piece of text or whether it's a pair of images, right? It's easy for me to express a relationship between them, whether they're similar or not, rather than saying, hey, this object should belong to this category. So think about the Google's knowledge graph, right? We have entities connected to each other. We have, let's say, images connected to each other. If you have problems in your startup where it's easy to specify this, right? I mean, sort of like collect all your data, but rather than actually annotating all of your data, it's easy to specify, here are some relationships, I think, that these sort of data points like look similar to each other and these don't. Then the graph representation gives you a great and powerful mechanism to exploit that. And they get away from like all the challenges that I mentioned, like all the hard work of creating annotating new data, because under the hood, it's actually trying to capture the structure which you're providing in a very seamless fashion, but then use that for the machine learning downstream. Here's an example. This is an image graph. So basically, what I'm trying to do here is like showing you a graph of edges and nodes. Nodes are images, and edges represent visual similarity between these images, right? So these two look like cars. Those two look like animals. And in this case, there's a car. So there might be like sort of cross connections between different cars. But if you look, we can map this into the semi-supervised learning paradigm by saying that in this entire, like there are like 4 + 3, 7 images. But rather than labeling all of them, I can just label one of those images. This is a car, that's a lion. Now, if I exploit the structure in this like graph, I can actually label in a probabilistic manner what the likelihood of a car or a lion is in every image in this graph. So this is the idea that we're trying to exploit. So the structure gives you some sort of similarity notion, and the underlying assumption is things that are similar should be labeled with the similar things, similar labels. So how do we do this? At Google, we do this like using the Expander ML platform. So there are a bunch of like papers and also blogs about this thing. But it's basically powering almost like ML products in every PA inside Google. And this does it at a scale probably may not be that interesting to you, like at like billions and trillions. But the same concept applies even on a single machine. You can run this thing even on a single machine to tackle your problems. And you can break the problem down into two concepts, right? So I said like we're all about doing graph learning. So first is like how do you convert your data to a graph? And then second is like once you have a graph, how do you learn with that? So graphs are not something rare. It's pretty easy to actually construct. The simplest instance is like a social graph, or a user graph, which you already have access to in many cases. You have notions of how users interact with other users or other properties, financial entities, etc. And you can define this as a structure. There are some graphs which actually you have to construct from scratch. For instance, you might have, let's say, embeddings or representations of images. In those cases, you can actually use those representations and then like generate pairs of edges. So basically, if I look at the car image there and car image on the top right, if I look at the embedding and compute some sort of distance between those two embeddings, then it gives me a sort of a measure of similarity between those two. The key is how do you do this when there are hundreds of millions of nodes or billions of nodes, right? Which is, I mean, today's world, that's actually a reality. It's actually very feasible to do this because there are fast approximation algorithms to even generate the graph. So the one point to note is you shouldn't spend all your energy and sort of computational resources on just building the graph, because that's not the goal, right? I mean, it might be a means to an end, but that's not the end goal. So you want to come up with fast and approximate methods. Like even if the method is not perfect, it's okay. So you want to actually do something very fast and efficient to generate pairs of edges. And there are a number of techniques to do this. OK, so let's take an example of how this would look. And this is a toy example. I mean, we actually use some of this for some of the conversational work. But let's say you want to build an emotion graph and learn what words or phrases represent emotion concepts. OK, so I'm going to start with words and phrases that I've extracted from, let's say, Twitter or messages or whatever application you have. Now, it's easy to find word embeddings, representations for those phrases, because many of them are already readily available in open source. Using this, I will apply the previous technique that I mentioned to generate a similarity graph. So based on the embeddings, awesome and great are connected to each other strongly. ROTFL and haha are connected to each other because they appear in similar contexts in sentences. Once I have this, now the learning basically can be very flexible. Let's say if you want to learn the concept of funny in this graph, right? I can label a single instance, like the word laugh, because it's pretty obvious to me that laugh means suggest something should be funny, right? And then propagate this information through the graph. And even though I've never ever seen the word ROTFL, or I don't know what it means, I can learn that this is associated with the same label. So this is the key idea here. This is, I thought I didn't have any equations on the slides, but the way the learning works is, apologies, ignore the middle box. But what we're trying to do is, like, once you construct the graph, even if it's a billion, trillion edge graph, whatever it is, you have some of those nodes labeled. And the labels are represented by this y hat. So those are actually the seed nodes, basically the ground truth. And what you're trying to do is propagate this information through the graph. And for every other node in the graph, you're trying to learn a probability distribution as to, OK, what label should it belong to, right? Is it a cat? Is it a dog? Or in this case, is it funny or not, right? And that's what the learning process is trying to do. Here's how the learning algorithm works in practice. So, and this is pretty intuitive. Like, if you think about it, like, imagine you have the graph structure. Let's say the red and the orange colors represent two different concepts. And you're trying to learn for the rest of the nodes what the probability of those concepts are. You start from this instance. And then the nice part about these algorithms are they're actually iterative. Just like, when you're building the deep learning model, you're not training in one shot. You're actually running multiple iterations. So what you do is you propagate, in the first instance, your confidence on the red is highest for this node, orange is highest for this node, and you propagate this to its neighbors. Now, the neighbor's confidence changes based on how closely associated it is to the red or the orange node. Its probability on the concept red versus orange shifts. Earlier, it had no clue. Now, it says it's probably more likely to be a red. And so the same concept repeats itself, right? And the further away you're going from any of the labeled nodes, your confidence should basically fall back to the prior. That means you should make no assumptions at all. So this is the sort of idea that you're using during the learning process. And if you take this to the previous example, is exactly what happens. So the first node is labeled as a car. It's strongly connected to the car images. So when you propagate, the confidence on those images for car concept increases. And then as you move further along the graph, this sort of diminishes, right? Unless there are more connections here, connecting it to the original node. Of course, this is great if you have, let's say, 100 examples, 1,000 examples. What happens if you have, let's say, billions of nodes and trillions of edges, right? It might not be that scale. It might even be 100,000. You don't want to have to load everything in memory and try to perform these operations on a machine. The nice part is you can actually distribute that. So you can distribute that on the same machine or across different machines. So the entire graph does not have to sit on the same machine. And there are also some other things we have to do to make it work for what happens if you're trying to predict not a classification problem, right? Basically, you're trying to predict it's the dog or not. And instead, you're trying to predict over, let's say, some rich space of labels. That means, let's say, it's a million space label. Why would you need to predict over a million labels? Imagine you're trying to predict whether a given concept A occurs and also another concept B occurs, right? So it's a combination of concepts. So a user is both a fraud and something. You guys have a better idea of what those other things are. But imagine you're trying to predict compositional labels, right? Now you can see that the number of labels exponentially increase. So there are ways to deal with that as well in constant time. So this is also from our published work. So all these things, the way to think about all these problems is you want to start with the small, the simplest instance of the problem, and then slowly scale it up. Is it a scaling of data, dealing with the data, the graph, or is it a scaling of the output complexity, or is it a problem of the model complexity? Think of that in iterations rather than here's the best model for this task, and I'll try to apply it to my data, right? Because if you do that incremental, you might actually come up with methods that are even far better than what's out there for your task. And this happens quite a lot. OK, so I spoke about graph learnings. How do we do this at scale, right? So this is one way to exploit the structure in the data and also get away from this challenge. I heard a lot of questions come up about how do we get the data? I mean, what happens if a new domain I don't have enough data or high quality data? So this is one way to exploit that structure. But quite often, if your task involves some prediction problems that are difficult, you also want like high capacity models at the end of that spectrum. That means you have to use deep learning or even other type of ML models, right? So you don't do graph, I mean, it's not necessary that you just do graph learning by itself. You could actually do it in one shot, learn all the annotations and say, pick all the high confidence nodes and say, okay, now I know for all my users, okay, they're fraud with probability X or 1 minus X, it's not. But you can actually build on top of that. So you can combine this with deep learning models as well. So before I get to how we do that, like if you think about why we actually use these models, as I said, graph learning is to capture some structure in the data to get over the data or other challenges. Deep learning and other ML models are basically trying to learn some predictive functions, going from some input to output, right? And they're pretty deep learning. Specifically, the neural networks are very good function predictors. Let's take some examples of where these two things like work in cahoots, right? Especially at Google scale. Smart reply is a perfect example of that. Like, so when we first introduced this, like we have a paper that details the method, but I will just give you like some sense of like why you need both of them. So in this application specifically, the goal is you're given some incoming conversation and you have to predict responses that are probably likely or good to as like a recipient would send to the original sender. And you want to show them multiple suggestions. Here, graph learning is used to sort of compress, let's say if you take the millions and billions of messages in the world, how do you cluster them into response intents? There might be 1,001 ways of saying thank you. THX, ... exclamation, all possible variants, right? I mean, you don't want to have to manually label each other and say, hey, this THX and thanks actually mean the same thing, right? So that's where the graph learning comes in. So we build a graph over the messages and also like related phrases, and then we do the learning. And what it does is it maps every message into sort of like some hundreds of response intents. And these are interpretable response intents. Like we can actually say, hey, if it says thanks, it belongs to some specific type of concept. And then the deep network, which is a sequence model, and if you're familiar with RNNs or LSTMs, so what it does is, like, in comes the conversation, it maps this, encodes this conversation, and then tries to pick a response, but from one of those intents that we actually discovered in the graph learning phase. So here's one example. So this is a query, hi, I thought it would be great for us to sit down and chat. I'm free Tuesday and Wednesday, and the response generated by the machine is actually, I can do Tuesday, I can do Wednesday, how about Tuesday, I can do Tuesday. You probably realize, okay, it seems pretty good for an ML system, but can anyone tell me what's wrong with that? Or what might be a problem if you show all these suggestions to a user?
Redundant.
Yeah, exactly. So how do you deal with that, right? So now if you look at those responses, like for a different message, can you join tomorrow's meeting? Again, the same problem manifests, but instead, if you look at the predictions and we already understood the response intents, we can actually enforce diversity. And so this is what you need. So it's not a single ML system that, you know, always produces the best output. We actually, in order to build a good user experience, we might have to actually combine different machine learning paradigms, different machine learning systems. So in this case, we know that the first two are different intents, or at least like slightly different intents, whereas this one is different, like sort of more negative. I can't make it, so. But all the other ones actually fall into one of those. So we are only going to show the three most diverse ones. So this is encoded. So basically, you're trying to learn semantic intents by using graph learning and deep learning. So the same thing appears in image classification. If you are using Google Photos, like all the last few generations of the object recognition models used in Google Photos and also on the cloud uses both of these systems in practice. And here the problem is slightly different. It's not for diversity. If we actually had to build a high quality system for Google Photos at the same quality that you're seeing right now, how much time do you think it would take if we wanted to label all the images that we have access to? 10,000, well, that's a pretty pessimistic update, but I think we can do it in a couple of decades. Probably the field and also, God knows, Google also would have moved on to a different thing right by then. So what we do is, like, we have access to, like, you know, hundreds of billions of images, right? But only a tiny fraction, let's say 0.5% sometimes, are labeled. So we actually use the semi-supervised learning and combine it with the deep learning methods to build a next generation systems. And here the key is like, because you're doing this, the deep learning system also learns in a much more efficient manner, because you don't show it all the noisy, like redundant and like useless images, right? I mean, you actually give it high quality data point. So it trains faster, but also the quality is also much better. Same thing with photo reply. I mean, the first generation of the photo reply system, and there you can think of like the goal is, just to show this example again, you have the image and you want to basically respond with, like, say, graduation picture means you want to say congratulations, right? One instance of a graph learning problem here is basically you have concepts in the image space, but you also have responses. Now, I don't know, those are all linguini or pasta images, but I don't know that the linguini is supposed to be yummy. So I can propagate this information through this graph and then like learn that, hey, linguini should be associated with the response of yummy. Well, this depends on what you see in the data, right? So if some people didn't like linguini, you might also see that as well. So, but the idea is like, how do you learn these concepts in a structured manner? Moving on, same thing for video summarization. Like this is I think this was like a really cool example. Like we had one of our interns work on this, and the demos were really cool. I wish I could have shown you the demo, but here's like one of the examples. You're given a query like salmon pasta cooking video, and this gives you like results on YouTube like of 1 hour long cooking videos. And most of the time the person is speaking, I mean, probably not even related to the cooking part, right? I mean, about personal lives. And now imagine you want to actually distill that information and say, okay, I'm interested in the most relevant concepts, or like if you show me a 20-second video of this, like, can it summarize the entire video, right? But the input is not just the video, but it also, like, say, some concept like salmon pasta or something like that. So what it does is it combines both deep learning, you're learning, so it breaks the video down into frames, and then the frames are processed using a deep learning system to build representations, and then you build like sort of a graph structure over these frames to see which ones are redundant, like do the graph learning on top of that, and at the end of the whole process, you're selecting different frames or segments in the video which are most relevant to the concept but also diverse, and then it strings it together in a sort of a seamless fashion to play like a GIF. Yeah, so I think the video for he was a big fan of Knight Rider, so he had like DeLorean and all the kind of like interesting videos and summarized, and there's a whole cache of these things. But it gives you an idea of like these are complex problems, but there are ways to actually exploit structure, and it seems like this seems like a horrible. Imagine if you had to build a annotator system to take every video in the world and like actually select frames and build a summary of that, right? Never going to work. So you need like techniques like these to actually think of new or build new applications. Okay. So hopefully this gives you sort of some motivation of like how we build these machine intelligence features at scale, and how we deal with some of the scalability and the data issues, right? So I spoke about two concepts: deep learning, graph learning. Now, if you're building any system, like ML or not, you start with building some component, and then you start building another component on top of that. And then like at some point you realize it's actually inefficient to take these two components and run them separately, right? You probably want to do this in a seamless end-to-end fashion. So this is what the notion of neural graph learning is. It's also a new research area that we're like powering in the ML community. But the idea is like, okay, if I have to do graph learning followed by deep learning, then can I do it in a single shot? And so one of the ways that we do this is what we call neural graph machines. So there are papers on this, and we are actually using it for a number of applications. But you can think of this as, instead of feeding pixels or features into your neural networks, you can now feed it graphs or structures. Imagine taking that user graph and then feeding that into a neural network and asking it to learn something interesting. So this is the idea here. I won't go into details of how we do this, but you could think of when you train any ML model, you're trying to optimize or define some sort of loss function and trying to optimize towards that. Here, the loss function has two components. Basically, one, learn a good predictor from, let's say, pixels to classes. And the second is actually respect the graph structure. That means like things that you tell me are similar in the graph structure should learn similar representations inside the intermediate layers inside the neural network. we think it's pretty cool, and we think it'll actually bridge both of the communities of graph learning and deep learning. So right now it seems like, hey, should I use this or that, right? I mean, so we think it's like a sort of a natural way to fuse the information and also power new applications. The good part is it doesn't depend on what architecture. If you take any neural network architecture, it works with all of those because it's basically parameterized as an objective function rather than the structure of the network. So you can have a feed-forward version of this. You could have a convolutional model that also does this, where, let's say, if you have image graphs, you can actually process using convolution networks and this objective function. You can have an LSTM version of this. We've done all of these variants, and like they actually give pretty good improvements. Here's some applications where this actually helps. So we've used it to predict like social graphs. Like for instance, you have a graph of users, and you want to actually predict some attributes for those users. You can actually feed that in and get like pretty good predictions. Now, one alternative way to do that is like take your graph and then try to learn something about the user attributes using the graph structure. Like that means featureize your graph, and then once you have featureized the graph, then you just apply to an existing ML system, the SVM or deep network. That's an approach. This one is basically trying to do it in a single shot. Text classification, categorizing documents, semantic understanding the intent, and low supervision. That means the emotion problem that I told you, where you want to learn some new concept. This is also possible here. Now, the key thing, one of the interesting findings here was that most people think it's the most complex or the biggest network that actually always produces the best performance. What we've been able to show is that for some of these tasks, like for instance, if you're familiar with the Yan LeCun, how many of you know Yan LeCun? So if you're familiar with the character CNN model that they introduced, they had like this 9 layers to get the performance. We were able to use like 2/3 of that depth and achieve the same performance. In some cases, even better performance. And so the idea is like exploit the structure in the data better, whether it's neural networks or any ML model, and that can actually help improve the performance. There are a number of ways to do that. This is one of them. OK, so the final part is we talked about addressing challenges in the data, the model complexity, how do you combine different types of ML paradigms. Another angle to this is there might be different computational models, right? You might have the best system on the cloud, but when you actually want to serve it on devices like wearables or even your phone, it can be very tricky. Especially you're super happy with this deep network model, and then you have to figure out, OK, how do I run this on the watch or the phone? And I'll tell you why you probably want to do that. In some cases, you don't. If you have enough bandwidth to actually make a cloud prediction or cloud call, I think that's the first option you should choose. On-device will be helpful in many settings where that's not an option, right? But in many cases, you actually want to do both computation on the cloud and on-device. You heard about on-device ML, at least some of the efforts that are going on in Google from Rishi. So I also lead some of those efforts that Rishi mentioned. So one of the questions we started, this was a couple of years ago, was like, just take the smart reply problem, right? I mean, the Android Wear team came to us and asked, like, hey, you have these great models for doing smart reply. Can we build that on the watch? And we're talking about gigs of LSTM models and then shoving that to a watch which has 750 megahertz and probably not even 1/10 of that like memory, right? So how do we do that, right? The reason for doing, first of all, the motivation for building such an application is pretty obvious, right? Like watches or phones are on you all the time. So if you actually get access to those predictive models, then it's very easy to make. I mean, it becomes useful like in crowded settings or even like settings where you don't actually want to go pull up your laptop and send responses. So imagine like with a touch of a button, right? You actually send a reply. So the general problem we try to solve is like, I'll focus on the inference part. The training, I'll get to it in a bit. So you're given some input, and you want the ML model to make all the predictions directly on the device. Device could be watch, mobile phone, IoT, Raspberry Pi, any of those sensors, health devices, etc. The reasons are manifold for doing on-device ML. Depending on your application, some or none may apply. Connectivity is pretty common. So if you're in emerging markets, right, you may not have access to like Wi-Fi or strong Wi-Fi all the time. So this is one reason to actually do ML on device. Privacy is super important. not all the users want the data to be streamed to the cloud, right? And in many cases, to be honest, you don't need to. If you are able to actually make a good prediction and build a good experience on the phone or on the device, that's actually enough. That's what they care about. And you might also benefit from that rather than streaming all the data and taking the payload and like storing it, logistics, etc. And finally, efficiency, right? Like, so they're making those RPC calls and coming back, etc. It becomes a hassle. Now, of course, this is easier said than done. There's a number of challenges, like I listed a couple of them here. Hardware is obviously one. Your phone is probably less powerful and slower than your laptop. Your laptop is less powerful than a machine, the server machine, which is less powerful than the entire data center. So you see the scale at which the computation changes rapidly, right? So how do you build these models and do those computations, like given the hardware constraints? Second is like you don't want to do or perform on-device ML if it leads to bad experiences. Just because you're doing on-device doesn't give you, or like any of us, right, the right to say, hey, yeah, this is what we can do, deal with it, right? I mean, users will say, I don't care. Come up with a better model. Thirdly, like it's trickier actually to build these complex models and combine them on device than server. And the server, it's like swapping out components and it's all abstracted out to the developer, right? But for you as like the companies, right? I mean, when you're building these, like it's harder to test and also harder to combine different systems. And it becomes more challenging as the task gets more complex, right? Like, predicting whether like some label is, or sorry, a user is doing action X or not is one thing, but like predicting something richer, like a response, is like slightly more challenging. So how do you do these things? So if you're interested, you could take a look at some of our work. I mean, there are more details in the blog, but like for Smart Reply, what we're able to do is we actually launched this feature last year in Android Wear. So basically, it's a system that and an API that's abstracted for any Wear developers. You can plug into that and pass in your conversation, and you will get like a set of responses back using an ML system. And if you're interested in how we do this, the key is like we have to come up with more efficient operations and architectures that can simulate what these complex models, LSTMs, do. There are a number of ways to do that. What we have is like a new method called projection-based neural networks, which says that if you're familiar with language or deep networks to language, the first layer is basically loading up some word embeddings or word representations. Now it's a huge matrix. Like you have to store that, there's no way around that. This basically gets away from that problem and says you can dynamically compute that on the fly. I know that doesn't say much, but if you're interested, like ask me later. And the cool part is you get these like really tiny networks that are almost 100 to 1000x smaller. And the performance is like maybe a couple of percentage points different from the original model, which is really cool. Even better, this is available for any Android Wear messaging app. So whether you're a big company, a small company, if you have an Android Wear app or a mobile phone app, you can actually plug into the API and get the predictions for free. So this is one way what we build at Google Research. We actually try to either open source it like through code or papers or like APIs which are seamless. There's also a TensorFlow Lite version of this available in open source, so it doesn't have to be Android Wear. Any device that you have, you can plug into this model. And finally, what if you don't care about Smart Reply, but you care about doing this for your own app, right? Like, let's say there's some specific task you're interested in. You can build your custom on-device models, and this is you can do this using the Learn to Compress framework that Rishi mentioned. We built this ground up. Right now, it supports a few use cases, but if you're interested in the alpha, you can please sign up. And the idea is you can upload data and or an existing model, and out comes either a single model or a set of models, which are all compressed and efficient. That means it runs faster, it's more power efficient, and it's also smaller in terms of memory. And this is available through the Google ML Kit for Firebase. So it works both in Android, iOS, and Android and iOS. So if you're interested, please check it out. So with that, I will close. Thank you for your time, and happy to take any questions.